In 1955, the average American 8th grader could multiply 3-digit numbers in their head, pull a square root out of a page with nothing but a pencil, and figure compound interest before the lunch bell. Today, most college graduates reach for their phone to split a dinner check, but here is the twist. Problem number 3 on this list hides a trap so clever that even engineers get it wrong on the first try. And number 1, it was a standard exam question in 1953, yet fewer than 1 in 20 adults can solve it now. These 20 problems came straight from the chalk-dusted blackboards, the time drills, and the red pen tests that shaped a generation. Before we start, hit that subscribe button and grab a pencil, because I want to know how many you can actually get. Let's count down from number 20. Number 20, the corn crop. Picture a one-room schoolhouse in the fall of 1954. Wooden desks bolted in rows, an inkwell in the corner of each one, and a teacher tapping the blackboard with a piece of chalk worn down to a nub. The first problem of the morning was pure multiplication, and every child was expected to work it clean. A farmer sells 347 bushels of corn at 68 cents a bushel. What does he earn? No calculator, no scratch paper if the teacher was strict. Try it before I show you. Here is how they did it. Multiply 347 by 68 the long way. 347 times 8 is 2,776. 347 times 60 is 20,820. Add them and you get 23,596 cents, which is $235.96. A tidy sum in 1954, more than a month's rent in many towns. The point was never the corn, it was the discipline of carrying every digit without a single slip. A child who reversed a 6 and a 9 or forgot to shift the second row one place to the left got that whole line crossed out in red and had to work it again at recess. That fear of the red pen is exactly why the answers stuck for a lifetime. Number 19, the apple crates. The second bell of the morning meant long division, and this is where a lot of modern folks quietly fold. A wholesaler ships 4,836 apples and packs them evenly into 12 crates. How many apples land in each crate? The 1950s student would set up that long bracket, the one that looks like a little house, and start chipping away. 12 into 48 goes 4. 12 into 3 won't go, so bring down the 6 to make 36. And 12 into 36 goes 3. The answer is 403 apples per crate. Exactly, no remainder. That neat 0 in the middle tripped up half the class every single year because you had to remember to write it down instead of skipping straight to the 3. Miss it and you'd answer 43. The teacher's red pen lived for that mistake. Number 18, Grandma's flour. Fractions ran the American kitchen and the American classroom in equal measure. A recipe calls for 2 3/4 cups of flour and 1 2/3 cups of sugar. What is the total? You cannot add these until the bottoms match. 3/4 becomes 9/12. 2/3 becomes 8/12. Add those and you get 17/12, which is 1 5/12. Now add the whole numbers, 2 plus 1 plus that extra 1, and you land on 4 5/12 cups. Every child learned this on the same worn textbook page, and every child learned that the common denominator was the whole game. Get the 12ths right, and the rest is easy. Reach for a phone today, and you'll get a decimal you can't even measure into a mixing bowl. Number 17, turning a fraction into a percent. Here's a quick one that used to be reflex. Express 5/8 as a percentage. The 1950s way was simple. 5 divided by 8. 8 into 5 won't go, so 5.000. 8 into 50 is 6. Carry the 2. 8 into 20 is 2. Carry the 4. 8 into 40 is 5. That gives 0.625, which is 62.5%. Children drilled the common fractions until they knew them cold. A half was 50%, a quarter was 25%, an eighth was 12.5%, and 5/8 was 62.5% without hesitation. That mental table is why a shopkeeper in 1955 could figure a markdown faster than you can unlock your screen. Number 16, money in the bank. Now we walk into the world of interest, and this is where arithmetic met real life. You deposit $200 at 4% simple interest for 3 years. How much interest do you earn? Simple interest is principal times rate times time. 200 times 4% is $8 a year. Multiply by 3 years, and you get $24. Every 8th grader knew this because every family lived by it. The passbook savings account was sacred. The interest was handwritten by a teller in careful blue ink, and a child who understood the formula understood exactly how their birthday dollars would grow. Schools even ran banking day, when students carried dimes and quarters to class and watched the totals tick up week by week. 4% felt like a fortune, and doing the math yourself faster than the teller could stamp the book felt like power. Number 15, the winter coat. Here comes a first little pattern break, the shopping problem, and everybody in class perked up because it felt like real spending money. A coat is marked $18, and it's on sale at 25% off. What's the sale price? 25% is 1/4, and 1/4 of 18 is $4.50. Subtract that from 18, and the coat costs $13.50. The smart students never multiplied by 0.75 and fussed with decimals. They just took 1/4 off in their head because they'd memorized that 25% means chop off 1/4. That instinct, seeing the shortcut instead of grinding the long way, was exactly what those daily drills were building. Number 14, the pencils. Proportion problems were the backbone of 8th grade word work. If 3 pencils cost 12 cents, what do 8 pencils cost? Find the price of 1 first. 12 cents split 3 ways is 4 cents each. 8 pencils at 4 cents apiece is 32 cents. It sounds trivial, but this humble skill ran the whole economy of a general store. Scale a recipe, price a bulk order, figure a fair share. It's all the same move. The 1950s teacher hammered find the unit rate until it became second nature, and a child who owned that idea was never cheated at the counter. Number 13, the mental math trick. This is where the class held its breath because the teacher would call on someone to do it entirely in their head. Square 35, no paper allowed. There was a trick, and every sharp student knew it. To square a number ending in 5, take the digit in front, which is 3, multiply it by the next number up, which is 4, and you get 12. Then just stick 25 on the end. The answer is 1,225. It works every time. Square 45, and you get 4 times 5 is 20, then 25, so 2,025. Square 65, and it's 6 times 7 is 42, then 25, giving 4,225. This wasn't cheating. It was pattern recognition, the kind of clever shortcut a bored kid in the back row would discover, whisper to a friend, and treasure for life. These little tricks were traded like baseball cards, and the student who knew the most of them was a minor legend at the chalkboard. Number 12, the report card. Averages showed up every grading period, so students knew them by heart. 5 test scores come in at 82, 76, 90, 88, and 84. What's the average? Add them all. 82 and 76 is 158, plus 90 is 248, plus 88 is 336, plus 84 is 420. Now divide by 5 and you get exactly 84. Simple, but loaded with meaning, because that number decided whether you passed. Kids learned fast that one bad score could be dragged up by 4 good ones, and that the whole class average told the teacher whether a lesson had landed. Mean, in every sense of the word, was personal. Number 11, the garden plot. Geometry lived outdoors in the 1950s, tied to real land and real fences. A rectangular garden measures 24 feet by 15 feet. What is its area, and how much fencing would it take to enclose it? Area is length times width, so 24 times 15 is 360 square feet. Perimeter is all 4 sides, so 24 plus 15 is 39, doubled is 78 feet of fence. Farm kids and town kids alike needed both numbers, one for the seed and soil, the other for the wire and posts. And notice the trap, because a lot of people confuse area with perimeter. The student of the 1950s learned to feel the difference. One covers a surface, the other wraps around it. Number 10. Miles and yards. Before the metric system was even a conversation in American schools, kids mastered the tangle of feet, yards, and miles. Convert 3 miles and 220 yards into yards. You had to have it memorized. There are 1,760 yards in a mile, so 3 miles is 3 times 1,760, which is 5,280 yards. Add the extra 220 and you get 5,500 yards total. That number, 1,760, was as familiar to a 1950s child as their own address. And here's a bonus most people forget. 3 miles is 5,280 yards, but 1 mile is 5,280 feet. Same digits, different units, and mixing them up cost points on every test. Measurement was memory, and memory was drilled. Number 9. 2 trains. Here's a second pattern break, and it's the most famous word problem in American history. Everybody groans, but here it comes. 2 trains leave stations that are 300 miles apart and head straight toward each other. One travels at 40 miles an hour, the other at 60. When do they meet? The trick is to stop thinking about 2 trains and start thinking about one gap closing. Together, they eat up 40 plus 60, which is 100 miles every hour. The gap is 300 miles. 300 divided by 100 is 3. They meet in exactly 3 hours. It sounds like a joke now, the punchline of 1,000 cartoons about math class, but this problem taught combined rates, the idea that speeds add when things move toward each other. That single insight powers physics, logistics, and half of engineering. The teacher would draw 2 little locomotives on the board, one at each end, and slide the chalk toward the middle to show the gap shrinking. Once you saw it that way, you never forgot it. The trains were never the point. Number 8. The nut mixture. The difficulty climbs sharply here, and this is where the room got quiet. A grocer wants to blend cheap nuts at 60 cents a pound with 20 pounds of fancy nuts at 90 cents a pound to make a mix worth 75 cents a pound. How many pounds of the cheap nuts does he need? Set it up by total value. The cheap nuts, call it X pounds, are worth 60 times X cents. The 20 pounds of fancy nuts are worth 1,800 cents. The final mix weighs X plus 20 pounds and must average 75 cents. So 60 times X plus 1,800 equals 75 times the quantity X plus 20. That's 60 times X plus 1,800 equals 75 times X plus 1,500. The difference, 300, equals 15 times X. So X is 20. He needs 20 pounds of the cheap nuts. Check it. 20 pounds on each side, worth 1,200 and 1,800 cents, is 3,000 cents over 40 pounds, exactly 75 cents. Mixture problems separated the strong students from the rest, and they were everywhere in real life, from blending coffee to cutting feed to mixing paint. The grocer who couldn't do this math in his head lost money on every barrel. The 8th grader who could was already halfway to running a business. Number 7, 2 pipes. Work rate problems were the terror of the 8th grade, and this is a classic. One pipe fills a tank in 6 hours. A second pipe fills the same tank in 4 hours. If you open both at once, how long does it take? Never, ever average the times. The trick is to think in fractions of the job per hour. The first pipe does 1/6 of the tank each hour. The second does 1/4. Together, that's 2/12 plus 3/12, which is 5/12 of the tank every hour. Flip that to find the time, and you get 12/5 of an hour, which is 2.4 hours, or 2 hours and 24 minutes. The gut says 5 hours, split the difference, and the gut is wrong. 2 pipes together must be faster than either one alone. The 1950s student learned to trust the math over the instinct. Number 6, the square root by hand. Third pattern break, and this one is nearly a lost art. Nobody under 60 remembers being taught it. Find the square root of 1,369 with pencil and paper only. The old method groups the digits in pairs from the right, 13 and 69. The largest square inside 13 is 9, whose root is 3, so 3 is the first digit. Subtract 9 from 13 to get 4. Bring down 69 to make 469. Now double the 3 to get 6, and ask what digit D makes 6D times D closest to 469. Try 7 because 67 times 7 is 469 exactly, so the second digit is 7. The square root of 1,369 is 37, dead on. Verify it. 37 times 37 is 1,369. Kids did this by hand every week. Columns of neat figures marching down the page like the long division they already knew, just with an extra twist. And here's the part that stings. This method was standard in American textbooks right up through the 1960s. And then the pocket calculator arrived, and it was gone within a decade. Today, the technique has vanished so completely that most people don't believe it exists, and math teachers themselves often have to look it up. A skill mastered by millions of 13-year-olds is now a museum piece. Number 5, the growing town. Now percentages get sneaky, and this trips up nearly everyone. A town of 5,000 people grows 10% in the first year, then 10% again the next year. What's the population after 2 years? The trap is to say 20%, giving 6,000. Wrong. The second year's growth is calculated on the bigger number. Year 1, 5,000 grows by 500 to reach 5,500. Year 2, that 5,500 grows by 10%, which is 550, not 500. So the population becomes 6,050. That extra 50 people is the whole lesson. This is how compounding works, whether it's population, debt, or savings, and the 1950s classroom taught it cold because families lived and died by compound interest. A mortgage, a savings bond, a store account that charged interest month after month, they all rode on this exact idea that a percentage of a growing number keeps growing faster. The student who understood it protected their family. The one who didn't got buried by it. The rich got richer on exactly this arithmetic, and the schoolhouse made sure every child at least saw how the trick was done. Number 4, the merchant's profit. Business math was woven into daily life, and every student could figure a markup in their sleep. A merchant buys a barrel of goods for $48 and wants to sell it at a 25% profit. What's the selling price? 25% of 48 is 12. Add that to the cost, and the barrel sells for $60. Simple, but the reverse of this problem is where people stumbled, and the teacher loved to spring it. If something sells for $60 at a 25% profit, the cost was not 60 minus 25%. You had to divide by 1.25, confusing markup on cost with markup on price cost. Merchants' real money, and the schoolroom made sure you never made that mistake with your own purse. Number 3, the round trip. Here is the trap I promised you at the very start, and it fools people with engineering degrees. A man drives 60 miles to another town at 30 miles an hour, then drives the same 60 miles home at 20 miles an hour. What's his average speed for the whole round trip? Everyone shouts 25, the halfway point between 30 and 20. Everyone is wrong. You cannot average speeds when the time spent at each speed is different. He spends more time going slow, so slow drags the average down. Do it properly. The trip out, 60 miles at 30 miles an hour, takes 2 hours. The trip back, 60 miles at 20 miles an hour, takes 3 hours. Total distance is 120 miles. Total time is 5 hours. Average speed is 120 divided by 5, which is 24 miles an hour, not 25. That single mile per hour is the difference between understanding averages and just guessing. The lesson underneath it is profound, that an average must be weighted by how much of each thing you actually have, whether it's time on the road, students in a class, or dollars in an account. Skip the weighting, and every average you calculate for the rest of your life will be slightly, invisibly wrong. A 1953 8th grader was expected to see the trap coming and step around it. Can you? Number 2, father and son. We're almost at the top, and the problems now demand real algebra, the kind that made or broke a student. A father is 3 times as old as his son. In 12 years, he will be only twice as old. How old is each of them right now? Call the son's age S. The father is 3s. In 12 years, the son is s plus 12, and the father is 3s plus 12. And at that point, the father is twice the son. So 3s plus 12 equals 2 times s plus 12, which is 2s plus 24. Subtract 2s from both sides and subtract 12, and you're left with s equals 12. The son is 12, and the father is 36. Check it. In 12 years, the son is 24, and the father is 48, exactly twice. Age problems taught a whole generation to translate plain English into an equation, the single most useful skill in all of algebra. Number 1, the clock. And finally, the problem that topped exams in 1953 and stumps almost everyone today. It looks innocent. It is not. At what exact time between 3 and 4 o'clock do the hour hand and the minute hand of a clock line up perfectly? Most people freeze immediately, and here's why it's hard. At 3 o'clock, the minute hand points at 12, and the hour hand points at the 3, which is 15 minute marks ahead. The minute hand has to chase it down, but the hour hand keeps creeping forward the whole time. Here's the elegant solution. The minute hand travels 60 minute marks per hour. The hour hand travels only 5 minute marks per hour. So the minute hand gains on it at 55 marks per hour. It needs to make up a 15 mark head start. 15 divided by 55 times 60 minutes gives 900 over 55, which is 16 and 4/11 minutes. So the hands overlap at exactly 16 and 4/11 minutes past 3. Not 16, not 17, but that strange, precise, beautiful fraction. And here's the detail that makes it unforgettable, the 11ths. The hands of a clock line up 11 times every 12 hours, never on a whole minute, always on some fraction over 11. Once a student understood that, the whole clock opened up like a puzzle box, and problems that looked impossible became almost mechanical. A 13-year-old in 1953 was expected to find it with a pencil, no diagram, no second chance on the timed test. Fewer than one adult in 20 can do it today, and most don't even know where to begin. So how many did you get? Be honest in the comments and tell me the exact number, because I want to see whether the round trip in number 3 or the clock in number 1 caught more of you. Drop your score below, tell me which one you'd have failed in 1953, and let me know if your grandparents really did math like this. Because here's the truth, they weren't smarter than us. They were just trained, drilled, and trusted to do it themselves. That's what we traded away for the calculator in our pocket. Grab a pencil this week and try just one of these on a kid you know. Then come back and tell me how it went.